About a year ago, I discovered that many researchers had a deception when they follow up a previously published work. So, why am I telling you that? My goal with this presentation is to inform you about the positives and negative points to release the electrodeposition of gold and platinum nanoparticles on flexible substrates as counter electrode for dye-synthesized solar cells. This work will be presented as follows. Introduction, functioning principle of a dye-synthesized solar cells, elaboration and characterization of the counter electrodes, and the conclusion. Recently, flexible synthesized solar cells have been developed by replacing the conductive glass substrate with the flexible substrate, such as conductive polymeric films for the working electrodes and the counter electrodes. This cell can be fabricated with low cost, lightweight, and less shape limitation. To develop flexible dye-synthesized solar cell, many groups have devoted their efforts to fabricate the nanocrystalline titanium oxide films, electrodes on the conductive polymeric substrates as the flexible photoanodes. However, less attention has been paid to study the flexible counter electrode. The energy harvesting mechanism is based in the absorption of the light by means of dye molecule anchored on the surface of a porous wide bandgap semiconductor. Electrons are injected into the conduction band of the semiconductor and collected at the transparent conductive oxide electrode. The cell is completed by a cathode converted by a thin layer of gold and platinum, and it is filled with an electrolytic solution that closes the circuit, regenerating the dye molecule. To obtain flexible counter electrodes with excellent electrocatalytic performance, in this work we would fabricate gold and platinum counter electrode using an electrochemical method by 40 successive cyclic voltammetry scans. As shown in the cyclic voltammogram, the reduction peaks of gold and platinum appeared at about the same potential, at a scan rate of 30 mV per second. Cyclic voltammograms were obtained in this electrolyte using electrochemical interface system at scan rate of 100 mV per second. The electrochemical cells consist of electrodeposited gold and platinum nanoparticles electrode as working electrode, a gold as a counter electrode, and an AgCl as a reference electrode. So, as shown in the cyclic voltammograms, the oxidation and reduction peaks of triodide were superior for gold and platinum counter electrode to the platinum electrode. However, the larger peak currents of triodide oxidation and reduction were observed on the gold platinum electrode, revealing that the electrocatalytic activity toward this kappa redox reaction at the nanoparticle of gold and platinum electrode was improved. Photovoltaic behaviors of the flexible dye-synthesized solar cell employing photoanodes, titanium oxides, and gold platinum counter electrodes are measured using a solar simulator under the peak illumination of 100 mW per centimeter. For the cell employing the platinized electrode, an energy conversion efficiency of 0.033% was obtained. However, the energy conversion efficiency of the cell increased to 0.061% by using the gold and platinum electrode. In the conclusion, gold and platinum nanoparticles electrodes exhibiting highly electrocatalytic activity for reduction of triodide is superior to platinum electrodes, and the comparison of the photovoltaic parameters indicates that the low energy conversion efficiency is mainly attributed to the resistivity of the used flexible substrate HIO. Thank you for your attention.